So this lesson is going to focus a little bit more just strictly on fractions. So this is going to be out of your book 2.1, 2.2, 2.3, and 2.4. So as we said in earlier lesson, fractions is a special way to represent a whole number and also the numbers between the whole numbers. So on your calculator, you'll be seeing these symbols n over d and un over d. And n and d are going to be really, really important in our vocabulary today. N is typically the numerator and d is called the denominator. And as we said, in understanding a fraction, the denominator is where the thinking begins. Then we focus our attention to that numerator. So when we have this 3/4, let's see if we can get this to work here. So we have this 3/4. Remember, the 4 means to cut into 4 equal pieces. And we have cut that in half and then cut each half in half. And there gives us our 3 slices, or now we have our 4 pieces. And 3/4 means you would take 3 of the 4 pieces. So that's what represent 3/4 of a whole. So you have to cut the whole into 4 equal pieces and then take 3 of the 4 pieces. On a number line, we kind of make what we call tick marks. So to do fourths, we usually just cut it in half, then cut each half in half. And that creates our tick marks in between 0 and 1. So remember, we would have 1/4, 2/4, 3/4 would be located at this spot right here on the number line. So it'd be a specific location, 3/4 units to the right of 0. Notice that's not quite a whole. Remember, 4/4 would be the whole. So 3/4, as we talked about with multiplication is what we call repeated addition. So 3/4 actually means 3 times 1/4. So 3/4 also means 1/4 plus 1/4 plus 1/4. So this is the expanded version of it. So notice the 3/4 is very compact. 3/4 really means 3/1/4. So when it comes to 2/5, notice how we have to cut something into 5 equal pieces. So 1, 2, 3, 4 slices. And again, those are supposed to be equal pieces. So we have to take 2 of the 5. So notice how we focus on the denominator and then the numerator. And that gave us our 2/5. So if I want to create these tick marks on an interval line, a number line, we have to cut from 0 to 1 into 5 equal pieces by using 4 slices. So 1, 2, 3, 4 slices, because the 5th slice is going to put us on 1. So 2/5 would be located at this position here. So 1/5, 2/5, 3/5, 4/5, and then 5/5 would be where 1 is. So again, mathematically though, 2/5 really means 2 times 1/5, or 2 1/5, which is equivalent to 1/5 plus 1/5. So that's kind of what it means. So fraction carries a lot of power in its notation to communicate a value. So some vocabulary we're getting in with fractions that are between 0 and 1, we have a special name for those. We call those proper fractions. The denominator will always be larger than the numerator in this situation. So examples of that would be, if I make the denominator 7, as long as the numerator is smaller, so if I put a 5 there, 5/7 would be a fraction that we would call proper, because remember, it would take 7 sevenths to equal a whole. So if 7/7 is equal to 1, then that means 5/7 has to be less than 1. So it is a proper fraction, because that would be between 0 and 1. Improper fractions is another vocabulary we'll come across. It's going to equal 1 or larger than 1. In this case, if the numerator and denominator are equivalent, we call this fraction equal to 1. If the numerator is larger than the denominator, this fraction is actually greater than 1. So improper fractions can also be written as what we call a whole number, or actually a mixed number. So we'll talk more about a mixed number here in a little bit. So notice that, 4/4, it means 4 1/4. So if we look at that, that's 1/4 plus 1/4 plus 1/4 plus 1/4. So if I'm using a number line, notice that I've already got my scale broken into fourths. So notice that we'd have 1/4, 2/4, 3/4, and notice that 4/4 would equal the same thing as 1. So notice that if the numerator and the denominator are equivalent, that will always equal 1. Now notice how I have 7 1/4. So 7 1/4 notice how if I go from 0 to 1, that's going to be 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4. So 7/4 will be located out at this spot right here. But notice there's another name for that. 7/4 would also be moving one whole and 3/4 of another whole. So 7/4 is equivalent to 1 and 3/4. So improper fractions can also be represented by what we call a mixed number. 10/5, notice that would be 10 1/5. So if I count by fifths, we have to have 1, 2, 3, 4, 5 tick marks. 1, 2, 3, 4, 5 tick marks. So each one of these tick marks is going to represent a fifth. So if I go 10/5, that's 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, 7/5, 8/5, 9/5, 10/5. 10/5 would put me out at this spot right here. That would be 10/5. But notice 10/5 puts you at the same location as 2. So 10/5 is equivalent to 2. So you start to see that, hey, fraction problems are sometimes just basically division problems. So notice that, 5 does go into 10 2 times. So you actually can simplify some fractions by just simply dividing them out. So when it comes to mixed numbers can be expressed as an improper fraction. So if I have 2 1/3, notice that 2 1/3 means 1 whole plus 1 whole because that represents 2, and then another third. Now remember, wholes can be expressed as fractions. So since my denominator is 3, I could change 1 to 3/3. I could change that other 1 to 3/3, and I have plus then this 1/3. So this one here can be the same thing as this 3/3 over here. So let's see here. So this one here can be the 3/3. This one is the 3/3. Then we have this 1/3. So what we have here is 3/3 and 3/3 and another 1/3. So notice how we're in the family of thirds. So if I break this into 2 slices, so 1/3, 2/3, 3/3, 1/3, 2/3, 3/3, 1/3, 2/3, 3/3. So now I have a scale tick marks going by thirds. So if I do 2 1/3, notice I can go 2 wholes and then another third. 2 1/3 would be located there. But also if I start from 0 and go to that spot by counting by thirds, we can kind of see that there would be, 1, 2, 3, 4, 5, 6, 7 thirds. So 2 1/3 can also be expressed as 7 1/3 or 7 thirds for short. So you kind of start to see some patterns here that, 3/3 plus 3/3 plus 1/3, notice that would be 7 thirds. So you kind of start to see the development of adding fractions. If the denominators are the same, all we're really doing is counting how many thirds are present. How many thirds are present is simply by adding the numerators together. So you kind of start to see that adding fractions is, as long as that denominator is the same, they're addable to simplify it down to a single fraction. So if I want to change each fraction to a mixed number, what we kind of talked about is we can change an improper fraction by actually using division. Such that I can do 5 into 8. Well, 5 would go in 8 one time. 1 times 5 would be 5, and I'd have 3 left over. So we would say this is 1 and 3/5. So 8/5 is the same thing as 1 and 3/5. Now, if I want to draw it out using a number line, I can also do it that way. That's kind of the long way. But that's how we're talking about fifths. So if I have 0 here, 1/5, 2/5, 3/5, 4/5, 5/5 would be 1. 1/5, 2/5, 3/5, 4/5, 5/5 would be 2. So if I have to go 8/5, notice that would be like, so if I use another marker here. So if I go, 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, 7/5, 8/5, that would put me at this spot right here. Notice that is the same thing as 1 whole and 1, 2, 3/5. So that would be equivalent. But notice how it's easier to actually divide. So when you do 5 and 8, you get the whole number up at the top. The remainder is going to be down here at the bottom. And then notice that this 5 becomes the numerator. So the 3 becomes the numerator and the 5 becomes the denominator. So if I want to do 27/10 back into a mixed number or whole number, what I would do is do 10 into 27. Some of these people, we call this, some of us sometimes call this what the rain game. The 27s get rained on, so we put it in the garage, and the 10 goes on the outside. So 10 does go into 27 2 times. 2 times 10 is 20. When we subtract, we would have a remainder of 7. So we'd have 2 and 7/20. Now all this, I'm sorry, 2 and 7/10. So all this can be done with the calculator, and we'll show you how to do that in another video. So if I want to change each mixed number into a fraction, the easiest way to do it is we start with the denominator. We just say 5 times 3 is 15, and then we add. So we kind of multiply here, and then we add the 2. That becomes my numerator, and we keep the 5 as our denominator. So 5 times 3 is 15, plus 2 would be 17, so this turns into 17/5. So this saves me the trouble of having to draw a number line and try to figure this all out. So, 3 and 2/5 means I'm here, 0. You have like 1, 2, 3, 4, 5/5 would be 1. 1, 2, 3, 4, 5/5 would be 2. 1, 2, 3, 4, 5/5 would be 3, and then 1, 2. So let's say 3 and 2/5 would be way over here. But how many fifths actually is that? So if we start over here at 0, it would be, use a different marker here, we'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Or you can go 5, that would be 5, that would be 5, that's 10. That'd be another 5, that would be 15, and then 2 more would be 17/5. So you can also do it that way. So let's say there's 3 5s. So in other words, 5 times 3 is 15. That's where this comes into play. Instead of counting by ones, we'd also count by groups of 5, because groups of 5 make one whole. So we have 3 of those. And then, so that's how we could do that using some shortcuts. So if I want to change 2 and 2/7 into an improper fraction, this mixed number, just multiply the 2 times the 7 and then add the 2. So we kind of go around the horn, and that becomes my new numerator. So 2 times 7 is 14, plus the 2 gives me 16. So 16/7 will become my improper fraction. So that's a little bit about introducing the different types of fractions that you may come across. Also, kind of changing between improper fraction and mixed number is kind of important. And that also is explained in a video, and you can do that on a calculator if you like to. But since this math is so small, it's really not the trouble. It's not enough trouble to pick up a calculator. So another thing we're going to get into is what we call multiples and factors. Multiples can be found by multiplying a number by 1, 2, 3, 4, 5, so forth and so on. So typically we list the first 5 multiples. So let's see, since, what's that mean? Hold on here. Don't know what that word actually is. So yeah, so typically we list the first 5 multiples since we see the pattern goes on to infinity. That should be since the pattern goes on to infinity. So since this goes on forever, we typically just list the first 5 multiples. So if I want to list the first 5 multiples of 11, well, 11 times 1 would be 11. 11 times 2 would be 22. 11 times 3 would be 33. 11 times 4 would be 44. 11 times 5 would be 55. You can also see 11s have a nice little pattern: 11, 22, 33, 44, 55. So I really don't have to actually multiply those out. A lot of times we kind of see that we have them right here: 11, 22, 33, 44, 55. So if I want to list the first 5 multiples of 25, since I can't name them all, so we know 25 is the first one, and then 2 25s is 50, 75, 100, and then 125 would be the 5th multiple. And again, they do go on and on, but a lot of times we will just list the first 5 multiples. It seems like that helps us solve a lot of the problems that involve multiples. So multiples are kind of familiar to us. Factors, on the other hand, are a little bit different. So factors are usually written as what we call pairs. The factor pair are the 2 numbers that multiply together to get, let's see, get my little picture out of the way. Okay, nothing there. To get the given number. If a number has exactly 2 factors, this number is called a prime number. If there are more than 2 factors present, then that number is going to be called a composite number. So these may be some vocabularies that we may come across again. Factors. And then there's special types of numbers: prime numbers and composite numbers. So to identify a factor, the number must be able to be divided evenly. When testing to see if the number is a factor, there can't be a decimal. So the answer needs to be a whole number and not a decimal. So if you're using a calculator to test using division, a decimal number on the calculator as an answer will signal that that is actually not a factor of the number. So let's look at these numbers here. List the factors of each, then define the number as a prime number or a composite number. So to do factors, I usually use what's called a T-chart. So kind of what I call big T. So I'm going to put big T underneath this 2. To do the factors, what I'm looking for are numbers that go into 2 evenly. So we always just start with 1. So 1 times what number gives me 2? In other words, 2 divided by 1 is what number? Well, that would have to be 2. 1 times 2 is 2, or 2 divided by 1 is 2. Either way we look at it, we get this number of 2 here. So 1 and 2 would be called a factor pair because 1 times 2 does give me 2. The next number I would look at would be 2. Notice that 2 times what gives me 2? Well, that would have to be 1. In other words, 2 divided by 2 would be 1. So that tells me that that is also a factor pair. But notice that it's the same factor pair, so we don't use it. So this number here has exactly 2 factors. If it has exactly 2 factors, we call this a prime number. So if we look at the factors of 3, we always start with 1. 1 times what number gives me 3? Well, 1 times 3. So notice that 1 and the number itself will always be the first factor pair. 2 times what gives me 3? Well, we know that 2 does not multiply to get 3, so that number's out. Then we'd have 3. Well, 3 times 1 would give me 3, but notice that that's repeating. So that tells us that we're done. And since there's exactly 2 factors, 3 is also called a special number. It's called a prime number because it has exactly 2 factors. If I look at the number 4, again, I'm going to use a T-chart. 1 times 4 is going to be the first factor pair. Then if I look at 2, 2 times what gives me 4, notice that gives me 2. But notice that I'm repeating at this point. So I see the factor of 2 repeats, so we can stop right there. So this has 3 factors. So this is actually called a composite number. It has more than 2 factors. So if I look at the number 5, we kind of see that 1 times 5 is 5. 2 is not a factor. 3 is not a factor. 4 is not a factor. 5 times 1 is, but also, again, we're just repeating factors. So again, since 5 has exactly 2 factors, we call that prime. So the question would be, is 6 a prime number? Does it have exactly 2 factors? If you can kind of see that, well, no, because to be prime, it has to be exactly just the 1 and 6. If there's any other factors, then it's not prime. And we would know that 2 times 3 would also be factors. And then, of course, 3 times 2, but that's repeating. So the factors of 6 would be just 1, 2, 3, and 6. It'd have 4 different factors. But since it has more than 2 factors, we would call that composite. 7. Notice that we'd have 1 and 7. That would be it. That's going to be prime. 8. We have 1 and 8, 2 and 4. That's it. That's composite. So as I move through here, we have 9. 9 would be 1 and 9, but we also have 3 and 3. So that's repeating. So 9 has 3 different factors, so it's still going to be considered composite. 10, 1 and 10 are not the only factors. So we know it's not prime because we also have 2 times 5. So that's got 4 numbers. So again, that is also composite. 11. Notice how we have 1 and 11. There's nothing else. So that's going to be prime. 12. Notice I got my cheat charts off a little bit here. 1 and 12, 2 and 6, 3 and 4, 4 and 3. So now that's repeating. So notice that would also be composite. And then 13, we have just 1 and 13. So again, 13 would just be prime. So notice there's actually only one even number that's prime, and that's the number 2. All the rest of the prime numbers are odd, but it's still kind of random at this point. So what are the first 5 prime numbers? We would see that, 2, 3, 5, 7, and 11 are some of the prime numbers that we see. So we have 2, 3, 5, 7, and 11. Those are the first 5 prime numbers. They do a lot of damage when I'm doing some of the math at a higher level. So they're kind of cool and help us decode some of the math before. So that's why we're talking about prime numbers, is they can create some shortcuts in solving more complicated problems. Prime numbers were also used back in the day as ways to disguise codes in some of the earlier wars before our new computers got so strong that prime numbers weren't enough. You had to create a much more sophisticated system to hide stuff with passwords and things. So divisibility rules, what we're talking about there is, how do we know if a number goes into another number evenly? If a number is even, in other words, if it ends in a 0, 2, 4, 6, or 8, that number will always be able to be divided by 2. So that's one of the divisibility rules. So like if I gave you the number 268, since it ends with 8, I know that 2 would go into it evenly. And if I don't know what that answer is, I could pick up a calculator and do that. But if I can see it, it looks like 134. Half of 268 would be 134. If you can see that, that's what we're talking about, using your brain for some of the shortcuts if you can see them. Another divisibility rule I'm going to talk about is the number that ends in 0 or 5. If a number ends in 0 or 5, we're talking about being divisible by 5. So if I gave you the number 105 divided, can that be divided by 5? I would have to say, yeah, because it ends in 5. If I gave you 1060, can I divide that number by 5? Well, yeah, because it ends in a 0. So if it ends in a 5 or a 0, I know 5 is a factor of those numbers. So remember, a divisor and a factor are synonyms. I just have to find the other pair, because factors usually travel with pairs. The last one I'm going to talk about is, if a number ends with 0, that means it can be divisible by 10. So like that 1060, since it ends in 0, I could say, hey, I can divide it by 2. Since it ends in 0, I could say, hey, that also divides by 5. And since it ends in a 0, I can also say divides by a 10. So that number there, we know is divisible by 2, 5, and 10. So we found a bunch of factors just knowing those 3 divisibility rules. So the next thing we want to do is write each number as a product of prime numbers. So the way I do this, again, I'm going to use a T-chart to do this. I'm going to use what sometimes I call big T, the T-chart. So again, I'm going to put this number above my T-chart. And remember, to find a factorization, I'm looking for factors. So I'm looking for numbers that multiply together to give me this number. But we're talking about prime numbers. So remember, our prime numbers are 2, 3, 5, 7, and 11. So doing this, I start with the first prime number, which is 2. And ask myself, is 2 a factor of 50? Well, since 50 ends in a 0, yeah, it has to be. So 2 times what is 50? Well, that would actually be 25. 2 times 25 would work. So now that I've brought the 2 out, I would stay with the 2 and ask myself, is 2 a factor of 25? Is 2 a factor of this 25 now? And no, 25 ends in a 5, so 2 is not going to work there. So that means I have to move on to my next prime number, which is 3. Does 3 go into 25 evenly? Does 3 times anything give me 25? If you're unsure, you can type that into a calculator, 25 divided by 3. And we would see that that's a decimal, so 3 is not a prime factor of 25. That brings us to the 5. 5 does go into 25 5 times. So we know that 5 times 5 is just going to be this 25. Now our attention turns to this 5. And we stay with the 5 until it doesn't work. But yeah, 5 does go into 5 one time. In other words, 5 times 1 is going to be 5. So once you get down to this 1, I've completed my prime factorization. My prime factorization is actually this product over here. So if I write those numbers as a product, I've got my prime factorization. So 2 times 5 times 5 would be my prime factorization. Or we could also write this as 2 times 5 to the power 2. since there's two fives there. So if I want to do a prime factorization of 625, we can start with 2, but since 5 is odd, 2 is not a factor of 65. My next number would be 3. I'm not sure about 3, so I pick up my calculator, 65 divided by 3, and that's not happening. I'm getting a decimal. So that brings me to 5. So I go 5 into 65. Well, that would be like 5 into 65. I don't have a calculator here for that. Sorry about that. So we do some long division. And 5 goes into 15 3 times, so 13. And we noticed that 13 was a prime number that we saw earlier. So we know that 7 and 11 aren't going to work, and 13 will. 13 will go into 13 one time. So when I get that 1 there, I'm done. So my prime factorization is actually this left-hand side. So my product or prime factorization is going to be 5 times 13. Okay. So another thing we're looking into is writing a prime factorization using exponents, as we did earlier. Let's just do another one of these. So again, we have 2, 3, 5, 7, and 11 are my prime numbers. So this 72, we're going to start with this 2. Well, how many 2's go into 72? Well, that looks like 36. So 2 times 36 would be 72. 2's prime, but is 36 prime? I don't think so, because it's even. 2 goes to 36 18 times. So 2's prime, but 18 is not prime because 18 is even. 2 goes into it. 2 goes 18 9 times. So 2 times 9 does give me 18, so we're okay there. So 2 again is prime, but 9 is not because I can use a 3 there. So 3 goes into 9 3 times. Now 3 is prime, 3 is prime. In other words, 3 goes into 3 one time. And that kind of concludes my prime factorization. So this side over here becomes my prime factorization. That's how I use a T-chart to organize things. So that means I have 2 times 2 times 2 times 3 times 3. But using exponents, there's 3 2's, so that'd be 2 to the third power times 2 3's. In other words, that'd be times 3 to the second power. And that would be a prime factorization using exponents. So another thing we're coming across is find the least common multiple of each number, or we also call that the LCM. So to find the LCM, there's a couple ways of doing it. Least common multiple just means the smallest multiple in common between some numbers. So if I look at the multiples of 4, 8, and 12, and I'm just going to write the 4, 8, and 12 like this and just list the multiples of each number. And a lot of times, all I got to do is list the first 5, and that will do the damage. So 4 times 1 is 4. 4 times 2 is 8. We have 12, 16, and then we have 20. The multiples of 8 would be 8, 16, 24, 32, and 40. Multiples of 12, 12 times 1 is 12, 12 times 2 is 24, 36, 48, and 60. So let's see if we can find any common multiples here. So I don't see 4 in common. I don't see an 8 in common. I don't see a 12 in common. I don't see a 16 in common. I don't see a 20 in common. So it looks like we have to keep on going here. So let's keep on going. So I have 24, 28. Let's see what we got going on now. That 24 looks like I'm already gotten somewhere now. It looks like there's a 24 here. There's a 24 here. And there's a 24 there. So it looks like our least common multiple would have been 24 by just listing the multiples. So our LCM turns into 24. So that's one way to find the least common multiple, is just list the multiples until you find one. A more advanced way of doing it is actually using a prime factorization. So for 4, we know that the prime factorization of 4 would be actually just, we don't actually need the chart here. I could probably do this in my head. These numbers are so small. So let's not even do this here. So 4, we know that 4 would be the same thing as 2 times 2, or 2 squared. 8 would be like 2 times 4, or 2 times 2 times 2. So that's going to be 2 to the third power. And then we have this 12. Well, that's going to be like 4 times 3, which is going to be, 2 times 2 times 3, using prime numbers. That's going to be 2 squared times 3. So once we write down the factors, and we don't want them to repeat here. So what are the factors here? What I'm seeing for the least common multiple, the factors I'm seeing, there's a 2 and there's a 3. So there's only 2 different factors, 2s and 3s. Once I do that, we use the largest exponent of each factor. So the most 2s I saw in common was 3. The most 3s in common were, that's just that 1 3. So if we put that together, we know that 2 to the third, really, that's just 8. 8 times 3 turns into 24. And that's another way I'd get my least common multiple. So what we do again is we write down the different factors, and then we use the most of each factor. Since there was 2 2s here, 3 2s there, 2 2s there, the most we saw was the 3. So we use that. And then the 3s, this is the one that had a 3, so we need it as well. So we have to do that to find the least common multiple. So that's the more advanced way, especially if the math gets more complicated, it becomes more useful. So next thing we want to look at is find the greatest common factor. So one way to do this is list the factors of each number. So again, if I use the T-chart, 18, I would have 1 and 18, 2 and 9, 3 and 6, 4 doesn't work, 5 doesn't work, 6 and 3. So those would be the factors of 18. The factors of 30, we have 1 and 30, that's a pair, 2 and 15, 3 and 10, 4 doesn't work, 5 does, 5 times 6, 6 times 5, that's repeating. So those are my factors of 30. My factors of 36 would be 1 and 36, 2 and 18, 3 and 12, yep, 3 times 12 is 36, 4 and 9, 5's not going to work, 6 and 6. So 6 is repeating, so those are my different factors of 36. So my greatest common factor would be the largest factor in common. Well, 1's in common, but is it the largest? 2's in common, 3's in common, 6 is not in common. So we're still at 3. 9, not seeing a 9. 18, I'm not seeing 18 in common. So it looks like the largest common factor would be, there's a 3, 3, and a 3. I'm not seeing any other common factors there among those. 6 looked, wait a minute, 6 was the largest, wasn't it? I missed it, didn't I? Shame, shame, shame. Can't read my own handwriting there. Missed it, didn't I? Hold on here, let me get this fixed here. Yeah, that's tricky about this. So I do see a 6 in common. 6 here, 6 here, and 6 here. Anything bigger than that? No, I don't see anything bigger than that. So I think we're okay this time. So the greatest common factor would be 6. Now, another way to do this, again, is do a prime factorization. These numbers are a little bit bigger, so I may go ahead and use my T-charts here. So I know 2 is a prime number, and 2 does go in that 9 times. 2 doesn't go into 9, but 3 goes in 9 3 times. And 3 does go in 3 1 time. So that's how I can break it down by using division. So I have 2 times 3 squared. 30. We have 2 again, 2 times 15. But 2 is not a factor of 15, but 3 is. 3 times 5. But 3 is not a factor of 5, but 5 is. 5 goes into 5 one time. So now we have 2 times 3 times 5. Now the factors of 36. 1, oh, sorry, we got use prime numbers. So remember, our prime numbers are 2, 3, 5, 7, and 11. They usually work. So we got to start with 2. 2 and 18. 2 times 9. 3 times 3 gives me 9, and 3 goes in 3 one time. So notice how we're kind of using division. 36 divided by 2 is 18. 18 divided by 2 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. It kind of makes that pattern across there. So again, notice how I did 36 divided by 2 is 18. 18 divided by 2 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. So if I write that down, I have 2 squared times 3 squared. So I can use the prime factorization to find the GCF. How does that work, though? What we want to do is only write down the common factors. So do they have a 2 in common? Yeah. Do they have a 3 in common? Yeah. So 2 times 3. Do they have a 5 in common? No. So only 2 and 3 are common. What I'm looking for now is the smallest exponent. So notice that this has 1, 2. This only has 1, 2, but this only has 2, 2. So the most in common would actually just be 1, 2. So I got that 1, 2 there. Now, the most number 3 is in common, or in other words, I'm looking for the smallest exponent. This has got 2, this is 1, that's got 2, but notice that they only have 1 in common. So I have just 2 times 3, which does turn into 6. So that's my greatest common factor. So that's how I can use a prime factorization to actually find what's called the greatest common factor. So it's a more advanced way of doing it. So next thing we get into is equivalent fractions and decimals. So one thing we have to remember is multiplying by 1. Multiplying by 1, the number or its value does not change. Now, there are infinite number of fractions equal to 1. So notice if I put 1 over 1, 2 over 2, 3 over 3, 4 over 4, 5 over 5, so forth and so on, all those fractions would equal 1. So as long as the numerator and denominator are the same, that's the same thing as 1. So to create an equivalent fraction, a fraction that means the same thing, what we do is we multiply a fraction by 1, but the 1 will have to look like a fraction. So if I want to, notice that if I have 1/2 times 1, that gives me 1/2. But notice that if I multiply 1/2 times 3 over 3, notice that again, 3 over 3 represents 1. So that actually represents a 1. Now, if I multiply straight across, though, this creates what we call an equivalent fraction. So 3/6 is my equivalent fraction. So 1/2, I got that actually wrong. This should actually be 3/6 there. Okay, not 1/6, but 3/6. So 1/2 is the same thing as 3/6. Those are equivalent. They mean the same thing. So when you multiply the top and bottom by the same number, this will always result in an equivalent fraction, a fraction that means the same thing. This is sometimes called raising a fraction to higher terms. So if I want to raise the following fraction to higher terms, all I got to do is multiply the top and bottom by a chosen number. So to keep it simple, I'm going to multiply the top and bottom by 2. That would give me 14/20. That would be an example. You could again multiply by anything you wanted to, so answers can vary. If I multiply the top and the bottom by 10, just choose a number. I chose 10. So I'd have 30 over 50. That would be an equivalent fraction. If I multiply the top and bottom by 4, doesn't matter what you multiply by, it's going to create an equivalent fraction. So that would be 8 over 12. That would be a fraction that would be the same thing as 2/3. Those would be equivalent. So that's what we call raising things to higher terms, is when you multiply the numerator and denominator by the same thing. Something else we want to get into is reading a ruler. Remember, it's about tick marks. So remember, if I count the tick marks here between 9 and 10, we have like, if I use a little bit lighter marker, so it'd be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It takes 16 ticks to get to the 10. That means each one of those little tick marks represents a 16. So if I count across there, I'm going to have like 1/16, 2/16, 3/16, 4/16. So that would be 9 and 4/16. But one of the things we learned, though, is 4/16 is actually a fraction that can be reduced by dividing the numerator and denominator by a common divisor, which would be 4. I haven't quite talked about that yet, but we will here in a second. But notice that we don't actually say 9 and 4/16. The appropriate way of saying it would be 9 and 1/4. So notice that this actually is a quarter mark here. That's a 1/4, and that's a 3/4. This mark here is actually the half mark. So that is 1/4, and this is 3/4, and this is the half mark. Okay. Some other things to point out is the tiny ones, these are like 16th marks here. So it's like 1/16, 2/16, 3/16, 4/16. I'm sorry, you count by odds. 1/16, 3/16, 5/16, 7/16, 9/16. So right there would actually be 9/16. Notice that the ones that are kind of between the quarter and the 16th, those are what we call the eighth marks. So there's like this one would be 1/8, 3/8, 5/8, and then that would be 7/8 if I'm using a ruler. So rulers actually have 3 different types of denominators. They have 16ths, eighths, quarters, and halves. So all those would work. So if I pick up on that, notice that, by the size of this mark, we're recognizing that's eighths. So we'd be counting by those. So it's going to be 1/8 and 3/8. So we would say this would be 3 and 3/8, since those are actually eighth marks based on the size of the tick. Remember, when you count mark to mark, you have to actually count by odds. That looks like the half mark. So that would just be 1 1/2 inches there. So we'd see that. So that's a little bit about reading a tape measure. You can go by 16ths, but in the end, that has to all be converted down to what we call lowest terms. So another thing we want to get into in this section is comparing fractions. It's actually easy to compare a fraction with the same denominator. The larger number will represent the largest fraction. I'm sorry, the larger numerator will represent the largest fraction in that situation. But if the denominators are different, the fractions can be written in higher terms so that the equivalent fractions have the same denominator. And then this would be called, a lot of times we would call this the least common denominator when we do that. So if I want to compare the following fractions to using higher terms as necessary, I can do that. But also on this first one, 5/8 and 3/8, notice how they both have eighths on the bottom. So 5/8 is actually more than 3/8. Now, using higher terms, I'd have to use it on this example because notice how we have a 5 and a 10. But notice how the least common denominator is also the same thing as the least common multiple. So if I have a 5 and a 10, notice that the next multiple of 5 is 10. So notice that 2 5s would make a 10. So if I multiply this denominator and this denominator both by 2, that's going to change the denominators to 10s. So this turns into 6/10, and this one doesn't change, it stays as 5/10. And how does 6/10 compare to 5/10? Well, it would also be greater than. So 3/5 is actually greater than 5/10. That's the conclusion that I can make from that. There's a unique strategy that I won't get into here as well, and that is you're allowed to what we call cross multiply. So if you multiply the denominator to the numerator in a diagonal, we call that cross multiplying. So 8 times 5 would be 40. 8 times 3 would be 24. Notice that the bigger answer is going to be the bigger fraction. So that tells us that the 5/8 is greater than 3/8. And we already knew that from the previous example. Notice if I do cross multiplication here, this way and this way, this also could tell me that if these are equal or not. Well, since this is 30 and this is 25, they're not equal. We recognize that 3/5 is actually greater than 5/10. So we can also use the cross multiplication strategy to determine whether or not the fractions are equal. So this is where we get into reducing fractions. Reducing fractions is when a number is divided by 1. But notice again, when we divide by 1, nothing changes. And there's a unique way to write 1 with fractions. Remember, as long as the numerator and denominator are the same, that represents 1. So if I look at the 6/10, I can try to reduce this by dividing by what we call the greatest common factor. So what factor do they have in common between a 6 and a 10? The only factor that I can see is actually a 2. So what we're going to do is divide the numerator and denominator by the GCF, which I think is 2. So 2 goes to 6 3 times, 2 goes to 10 5 times. And here I don't see a common factor except for 1. And if you divide by 1, it doesn't do anything. So that's how we can reduce fractions, is divide by 1. But we're dividing by 1 in a unique way. We're making the 1 an actual fraction. And we divide the numerator and denominator by that. And that creates a fraction that means the same thing, just in what we call lower terms. So if I'm looking at a 12 and a 50, I can't really see the greatest common factor necessarily because those numbers are so big. So sometimes I just pick a common factor. Since they're both even, I'm going to divide the numerator and denominator by a 2. Okay, because I'm not really seeing anything else at this point. So if we divide the numerator and denominator by 2, since they're both even, 2 goes into 12 6 times, and 2 goes to 50 25 times. Oops. 25 times. Well, no wonder that is it. So there's not, that's the only common factor there, because 6 and 25 don't have any common factors, because a 6 is made up of a 2 and a 3, and a 25 is made up of 5. So there's no other common factors. Now there's another way we can do this, and that is we can rewrite the numerator and denominator using prime factorization. A lot of times what we do here is we divide or cancel out the like factors. So if I was doing this problem, 12 over 50, I could do a prime factorization of the numerator and denominator. So remember, my prime numbers are this 2, 3, 5, 7, and 11. So 2 does go into 12 6 times. 2 does go into 6 3 times. 2 doesn't go into 3, but 3 does go into 3 1 time. So my 12 turns into a 2 times a 2 times a 3. My 50, if I use a prime factorization on it, again, 2 does go into 50 25 times. 2 doesn't go into 25, 3 doesn't go into 25, but 5 does go into 25 5 times, and 5 goes into 5 1 time. So I can change the bottom to 2 times 5 times 5. And from there, we just divide out like factors. So this 2 and this 2 would divide out. I don't see any other like factors, so we put it all together, and we have 6 over 25, and that would give me the lower terms reduced fraction doing it that way. So using factorizations can be a neat tool to do problems that are a little more complicated if need be. So when comparing decimals, the largest left place value will determine the largest number. So notice that if I'm comparing 3.125 to 4.01, notice that the 3 and the 4 is the bigger place value. So that already tells me that the 4 is the greater value. So 3.125 is actually less than 4.01. So if I have 3.69, I want to compare it to 3.64. Notice that the 3's are the same. The 6's are the same. But the 9 and the 4 are different. So that makes the 3.69 greater than the 3.64. So that's the larger one. You can also place or remove trailing zeros so that the numbers go out to the same place value. So if I have like 0.1265 and I have 0.8, I can also add on some more zeros here. So that's like 1,265, and this is like 8,000. So that's kind of telling me that that's bigger. So if I'm ignoring the decimal. But also notice that place value, a 1 and an 8, the 8 is bigger. So this goes out 3 places past decimal, so I can also make this one go out 3 places past decimal. Well, that makes them equal. They have the same value. So another topic we get into is adding and subtracting fractions. There's only meaning if the denominators are the same. Only add the numerators and then just keep the denominator when we are adding what we call like fractions. Use the LCD to add or subtract fractions with different denominators. Again, LCD stood for the least common denominator. So notice if I have like 3/8 plus 5/8, that's going to give me this 8/8. But notice that 8/8 is the same thing as 1, so that would just simplify down to 1/2. Look at this next example. Notice I have 2/3 plus 1/4. Notice how I wrote them down the page instead of across the page. I do this because my denominators are not the same, so I come out here to the side and write my denominators down 3 and 4. And I'll list the multiples of each one. So 3 times 1 would be 3, 3 times 2 would be 6, 3 times 3 would be 9, 12, 15. 4, 8, 12. So by listing the multiples is good enough. I didn't have to do a prime factorization there. So 12 is my new denominator. So I go out to the side and write my 12 as my new denominator. And then what I got to do is multiply the numerator and denominator by the number that creates the 12. So this is what we call raising to higher terms. So I got to multiply the denominator by 4 and multiply the numerator by 4 because I need that 12. So 3 times 4 gives me 12 and 2 times 4 gives me 8. So what I'm doing is renaming the 2/3 to 8/12, which is an equivalent fraction. In doing so, I still got to multiply the 4 down here by 3, and I got to multiply the numerator here by 3 to keep it equivalent. So 1 times 3 is 3, and 4 times 3, of course, is 12. Now, if I add these fractions together, 8/12 plus 3/12 gives me now 11/12. And 11/12 does not reduce. So if I'm subtracting fractions, and also if I have 14 and 1/7, if I want to take away 12 and 3/7. Notice here, we actually have to do some borrowing because I can't go 1 minus 3. So what we have to do is we actually have to borrow a whole from the 14 to make that 13. And what you got to do is you have to add the 1 to the 1/7. So this becomes 13, and then this becomes 1 and 1/7. And then we have minus this 12 and 3/7. This 1 and 1/7 has to be put into a fraction form since right now it's a mixed number. So 7 times 1 plus 1 would make 8/7. So this turns into 13 and 8/7. And then we have minus 12 and 3/7. Now this problem is workable. 8/7 take away 3/7 would be 5/7. And then 13 minus 12 would be 1 and 5/7. So some of this starts to take up time, and we start to take advantage of calculators to do that. So I modeled that using the graphing calculator in subtracting fractions. When multiplying fractions, a lot of times we'll pick up on this word of. The word of implies multiplication. So if I have half of 20, that means the same thing as 1/2 times 20, or 20 divided by 2. So half of 20 or 20 divided by 2 would be 10. So when you multiply a fraction times a whole number, there's actually an easy little pattern here that we pick up on. So there's a couple things that I'm talking about here as well. When multiplying fractions, you can multiply straight across. Also, a whole number can be written as a fraction by pasting a 1 underneath. So another way we could be talking about this is if I have like 1/2, if I want to multiply it by 20, I could put this as 20 over 1. So notice how this is really what we can do now is write this as 20 over 2, and then reduce would be back down to 10. So we can multiply straight across in that sense as well. Something else we can pick up on when multiplying a whole number by a fraction, start with the denominator, divide it into the whole number. If it goes into it evenly, then continue on and then multiply the new number by the numerator. So if I want to do 2/3 times 15, because of means multiply, what we do is we start with the denominator and ask ourselves, does 3 go into 15? Well, 3 goes into 15 5 times. So what I do is I'll mark those both out and write my answer of 5, and then we multiply the 5 to the remaining number. 2 times 5 would be 10. So 2/3 of 15 would actually be 10. If I want to do, let's see if I got any other examples there. I think that was it. Okay. So another thing we get into is dividing fractions. If I have 5 divided by 1/2, remember, division is the same thing as changing it going backwards, making it multiplication. So if I have 5 divided by 1/2 equals something, if I go the other direction, I could say something times 1/2 is equal to 5. In other words, how many 1/2s does it take to get 10? So, I'm sorry, how many halves does it take to get 5? So if I have a 1/2 and a 1/2, that's going to be 1. A 1/2 plus a 1/2, that's going to be another 1. So a 1/2 and a 1/2 is going to be another 1. And a 1/2 and a 1/2 makes another 1. Can I see where I'm going with this? And a 1/2 and a 1/2 gives me another 1. So that's 5 ones. So that means I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 10 1/2. So this answer's got to be a 10. So 1/2 times 10 would have to be 5. And of course, half of 10 does give me 5. So what I pick up on is that seems a little bit much. So there's actually a quicker strategy. The strategy comes from what we call multiplying by the reciprocal. The reciprocal kind of means to flip a number. So in division, this means, like I said, when we divide fractions, we're going to be flipping the divisor. So if I want to make this problem workable, if I have 5/8 divided by 5/4, to make this problem workable without a calculator, what we do is we write this as 5/8. Instead of dividing, what we do is we multiply by the reciprocal of 5/4, which is 4/5. Sometimes we call this Kentucky chicken fry, which stands for keep, change, and flip. So we keep the first number, change the division location as long as we flip the second number. And then all we got to do is multiply straight across. But before we do that, we can also do some canceling. Notice that the 5s can divide out. Those are like factors. Notice that the 4 and the 8 also have a common factor of 4 in them. So 4 goes to 4 one time, 4 goes to 8 twice. So I can divide out common factors there and make that a 2. So only thing we have left here then is really 1 times 1 is 1, and 2 times 1 is 2. So that turns into actually 1/2. Again, we can also use a calculator to divide fractions. So if I was going to divide these two numbers, the first thing I have to do is make this an improper fraction. 2 and 1/2, I could change to 5/2. And I'm dividing it by 2/3. But the key is actually not divide by 2/3, but divide by its reciprocal. So that's really going to be 5/2 times 3/2. So again, we call that Kentucky chicken fry, keep, change, flip. Keep the 5/2, change division to multiplication, and flip the 2/3 to 3/2. I don't see any like fractions, so I can just multiply straight across and call this 15/4. Now, since we're dealing with mixed numbers, they may want to change this improper fraction back to a mixed number. So 4 and a 15. 4 goes to 15 like 3 times. 4 times 3 is 12. 15 minus 12 is 3. So that's going to be 3 and then 3/4. So I could also say 15/4 or 3 3/4 would also be an acceptable answer. So that's dividing fractions. So that kind of gives you a nice marathon coverage of some fractions. So hopefully you found that useful in dealing with it. And like I said, some of the key things is some of this vocabulary, especially at the very beginning when we talked about factors and multiples, greatest common factors. Some of that vocabulary early on is going to be important as you do your homework. So not as much as the operations, because the operations can be done on a calculator. So yeah, multiples, prime factorizations, things like that, we may want to pay more attention to. So have a good day.